Hello everyone, welcome to the first lecture of this short course titled Behavioral Theory of Systems with a View Towards Data-Driven Control. So first let me explain what the meaning of the title is. We start with this idea of data-driven control first. So our idea of systems involve, mostly systems with inputs and outputs, right? So usually we depict a system as a box like this, which receives input signal and produces output signals, right? And this input and output are related with each other through systems governing equations. That's the standard description. That's the standard description of a system, right? Often we say governing equations, right? But nowadays, and how does one get these governing equations? Usually these equations are got by doing some first principle analysis, right? Which are also known as modeling. You look at the system, yeah. If you have information about the systems, what is there inside this box, then you look at those components and you write down equations from basic laws of physics, right? Those are your system's governing equations. But nowadays things are changing. Systems are becoming much more complex than before. Yeah, and it is becoming a really challenging task to obtain a systems equations by looking at the inside of the system. However, what we have now, at our disposal are these huge computing machines where we can feed data and obtain various information out of those data. Now one can ask this question that what if for a system I measure its, say, input output data or all the other signals that are there, which we will call as systems variables. What if we look at the system's variables, yeah, and we run the system and we obtain the data about these variables. For example, for this system, what if I get this input and output signal for a particular case? Perhaps I can get this input and output information for several cases, yeah, and that constitutes my data. Is it possible to define the system with just this data? Yeah, that's the basic question. Further on, is it possible? If it is possible to define a system out of just this data, would it be possible to do control of the system based on this data? Those of you who have done a little bit of control theory would know that for such a black box, we often put, a feedback loop with a controller. Right? With a controller. Yeah. Now, if you don't have information about the system's equations, if you have done a little bit of control theory, you know that in order to design a controller that achieves the desired goal of the overall system, you need to know the system's equations. With the help of these systems equations, you can then design your controller. It could be a PID controller, it could be a PI controller, it could be a state feedback controller, it could be an output feedback controller, it could be a dynamic controller. All sorts of controller designs are there. The theory about design of these controllers have been there for the past, decades. However, if we ask the question that if we do not have information about the system's equations, but rather we have only the data in the form of the input output for some cases, for some cases of running the system, is it possible for us to design a controller? This idea in particular is known as data-driven control, which of course, as you can understand, is has arisen from this huge boom that we are seeing in our computing power. Yeah, using large scale computing machines. Is it possible to have complex systems and their data and then design controllers based only on this data? But that, this question fundamentally brings us to this question, that is it possible to define systems using only data? Yeah. So that is where this first, the title of this course, this is the subtitle of this course, and the title of the course is Behavioral Theory of Systems. So behavioral theory of systems is one such, let's say, description method or a philosophy of describing dynamical systems, yeah, which is such that it allows us to define systems based on the data, and then it also gives us a framework in which we can understand ideas of data-driven control in a nice and unifying manner, right? And that is what we are going to learn in this course. Okay, so first things first, we are going to understand what is meant by behavioral theory of a system, right? So first, we take a very broad point of view, and we try to define system from the broadest possible point of view, right? So let us just ask ourselves this very fundamental, basic question: that what is a system? How do you describe a system? In mathematics, one of the most fundamental objects is sets, right? Is it possible now to define systems as just sets? Let me try to give you an example. Through that example, let us try and understand whether this definition of systems is somewhat meaningful or not. Okay, so the example is, let's say we look at water and its temperature, and then we ask the question about the state of water at these various temperatures. So what are all the possibilities? All the possibilities is defined by this set which we call the universum. The set of all possibilities. How do we define it in this case? All possibilities are, from this set, the water is either ice, or it is water, or it is steam. And what are all the possibilities of temperature? The temperature, all the possibilities for temperature is minus, okay, we are not being very precise as far as physics is concerned, but we are saying minus 273 degrees Celsius up to any positive number. So this is the universum. Yeah, we have two variables here. One is the state of water, which perhaps, let's say, we call it by, say, xi. Right? Let me write the xi properly. Xi is a variable which denotes the state of the water, and tau is the temperature. So xi can take values either ice or water or steam, whereas tau can take any value between minus 273 degrees C to infinity. Ideally I should not write degree C. It is the value, the degree C should be outside. Yeah, but let's not worry about this much. I hope you understand what's going on. This is the universum. And then we argue that the natural phenomenon, which is the system, tells us that physics restricts all possibilities to a set that is really possible, allowed by the laws of physics. And that subset of the universum is what that describes the system, and we say that this is the behavior of the system. We denote it by this Gothic letter B, and we call it the behavior. Right? And how do we define it? In this case, there are only these possibilities. You see, it's ice, comma, minus 273 to 0. Right? That's one possibility. Then we have water, and water can remain only through 0 to 100. Yeah, and the third possibility is steam, comma, 100 to infinity. You see, from all these possibilities, we have brought it down to these three possible cases, and that's the behavior of the system. So you see, in this sense, every system is actually given by a set of exclusion laws. Right? And the set U, that is the universum, this set is all possibilities, that's the universum. And then the system is given by the behavior, the behavior, which is the result of applying those exclusion laws and getting the behavior, indeed, of the system, right? Let me give you one more example so that this becomes even clearer, and something that we have done, all of us have done in high school, namely planetary motions, right? Now, in the planetary motions, if you look at suppose in our planetary system, there is one sun. This is the sun. Oops, my drawing is horrible. And then there is this planet, perhaps our Mother Earth. This is the planet. And then what I'm interested in is, okay, suppose this is my origin, because we know that in reality, I mean, it's a heliocentric model. I'm sure you have heard this term. That means sun at the center, literally. So we have sun at the center, so there's no harm in calling that this is my origin O, right? And then I can connect the origin of the sun, I mean the center of the sun with the center of the earth, and I can say that, okay, this radius vector, the position of the radius vector is q, and all of us know that there is this force of gravitation between, there's this gravitational pull between these two objects, and suppose the gravitational pull that Earth experiences due to the sun is, say, F, right? So then there are two variables in this system, right? F is a variable which takes values in R3, okay, at any point of time, and Q is also another variable, that is the position of Earth with respect to the sun, and that also takes a value in R3. I hope you understand the meaning of this R3. For me, R means the set of real numbers. The set of real numbers. I hope you know the meaning of real numbers, right? If not, then please look up basic maths book, and the symbol for that is R. Okay, so I have this f and q, two variables, and both of them are coming from R3. So now it's anybody's guess that the universum in this case must be nothing but, you know, the so-called Cartesian product of R3 with itself. What is meant by this? This is the set of all possible q comma f, because they can take any, q can take any value from R3 and f can also take any value from R3. That's why the universum is this. What is the behavior in this case though? Yeah, can anyone tell me what would be this behavior? Well, you see, for this force and this position, you know, arbitrary force and position is not possible. There is some exclusion law that allows some things to happen, you know, and it excludes other possibilities. And what is that? Well, of course, if you have studied your physics well in your high school, then you know that the law that governs this system is Newton's laws, Newton's laws of gravitation. What does it say? It says that the force that Earth experiences, the value of the force that Earth experiences, yeah, is G m small m capital M, where this is the mass of the Earth, mass of Sun, by the distance squared. That's the magnitude of the force, right? If you want to get the direction of the force, then you can do the following. You can notice that the force will be the force that the Earth experiences is in fact directed this way, right? Whereas the radius vector is pointing this way. So it's minus q in the direction of minus q. So in that case, I can modify this equation and put a minus here and put a q cube here and write q here. That's the relation that f and q must satisfy, yeah, as vectors. So therefore, in this case, the behavior, now you see all possible pairs of, you know, three tuples of real numbers is not allowed by the system. Yeah, what is allowed? Only those q and f will be allowed such that they satisfy this equation. Okay, so that's the behavior of the system. All right. Now, where does this take us? Yeah. Well, you see, the interesting part here is that although there is this equation for the system, but you see, these equations are not the ones, are not the most important thing about the behavior, about the system. The system gets defined by this behavior, yeah, which is a subset of all possibilities. So it's a subset of the universum, right? It's a subset of the universum. These equations define the behavior, but as we will see in future in this course, that these equations can change, yeah. Yeah, for the same system, the governing equations can be different, which result in the same behavior, right? So it is the behavior that is fundamentally attached to a system, yeah, and then one gets the equations that defines the behavior, that governs the governing equations that give us the behavior, but there is nothing unique about these equations, because those those equations are not, in many cases, are not uniquely attached to the behavior, to the system, right? Let us try and see an example of such a situation where we have different equations that can lead to the same behavior, right? And then we will proceed further to expand this idea of behavior and deal with the kind of systems that we are interested in various engineering problems, various control theoretic problems. Okay. So once again, something from electrical engineering. I'm sure all of you are aware of the kind of circuit that I'm going to draw now. Okay, so this is a bridge circuit. This is the voltage at the terminal. This is the current. Okay, this is resistance number 1. This is resistance number 2. This is resistance number 3. This is resistance number 4. Okay, let me also put some new variables. This is current I1. This is current I2. This is current I3. This is current I4. And likewise, I have plus minus V1, the voltage drop across this resistor, V2, plus minus V4, and plus minus V3. Okay. Now the variables that I am interested in is this V and I. These are the two variables that we are interested. These variables will be called manifest variables. Manifest as in something that is seen, yeah? So these are manifest variables. For us, they are the variables of interest. Manifest variables. But I have these several other variables, in fact 8 other variables, namely I1, I2, I3, I4, yeah, and I have corresponding voltages or the voltage drops. These 8 variables will be called latent variables. Yeah, these are important only as far as writing the equations for the system is concerned. Yeah, for the equations they are important, but the behavior for the behavior they are not. Right. So what do I mean by that? So here you see my universum is interested only in this Vi. Yeah. So therefore, my universum is in fact all possible pairs of real numbers, namely V and I. Right. But there is this latent universum, we call it UL, and that is R to the power 8, where these guys can take various values. Yeah. What are the system's laws? What are the system's equations? Well, they come from the voltage current Ohm laws, Ohm's law, and there is Kirchhoff's current law and Kirchhoff's voltage law. These laws together will give us all the equations. So perhaps I can quickly write them down in the next slide. Just bear with me for a while, and if I make a mistake, please be careful. If I make a mistake, then correct me. Okay. So first, Ohm's law. V1 equals I1 R1. V2 equals I2 R2. V3 equals V3 equals I3 R3, and V4 equals I4 R4. Okay? Right. Then Kirchhoff's current law. What do we have for Kirchhoff's current law? Well, first thing is I equals I1 plus I2, I apply Kirchhoff's current law here. You can see that, right? Yeah, at this node, okay, this node, and I get I equals I1 plus I2, right? What else? I get that I2 equals I4, I2 equals I4, and I get likewise that I1 equals I3, right? And finally I get I equals I3 plus I4, right? And then I apply KVL. What do I get? If I apply KVL, I get, okay, KVL around this loop, starting from here, moving through R3, and then moving through R1, and then this point. What does that give me? That gives me V equals V1 plus V3, right? And then another equation is if I move from this point to through like this through R4 and R2 and then like this at this point, I get V equals V2 plus V4, and then I can also apply KVL across this loop, and that will give me, okay, V4 plus V2 minus V1 plus V minus V3, which is another way of saying V1 plus V3 equals V2 plus V4. You see, I have not worried about which equations are independent and which are not, but I've written down all these equations, right? So these are systems equations. So what is my behavior then? All possible, B full is the behavior of all these Vi, V1, I1, V2, I2, V3, I3, V4, I4, this 10 tuple, such that these equations, let me call them the star equations, that all these star equations are satisfied. Yeah, that's the B full. So what is the behavior then? The behavior then is the following. The behavior then is the collection of all those VIs such that there exists this V1 I1 dot 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 up to V4 I4, yeah, in the universum of the latent variables, such that together this and this belongs to the full behavior, right? Together Vi, V1 I1 dot 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 up to V4 I4, this 10 tuple is in B full, right? Okay, and you see, as I was saying, because I have not looked at independent equations, there are too many equations. I don't need these many equations. I can actually describe the same behavior with lesser number of equations. Yeah, I have to just get rid of some of these equations. Like for example, I equals I1 plus I2 and I2 equals I4, I1 equals I3, then this equation is redundant. I don't need this. Likewise, once I say this much, right, this is and this much, this becomes redundant, right? But even if I keep this, the behavior doesn't change. So the behavior is independent of whether this equation is there or not. Likewise, I'm saying these guys are redundant, but I can actually decide to get rid of other equations, right? So therefore, the system's behavior is the one that describes the system, right? And not the equations. So the point that I'm trying to make here is that this behavior is the one that is uniquely associated with the system and not its equations. Yeah. So this much now for this lecture. In the next lecture, what we will do is we will take this idea further to incorporate what are known as dynamical systems, which forms the backbone of systems and control theory. Yeah. So how to get this basic idea of behaviors that are related uniquely with systems, how to extend this idea of behaviors to dynamical systems. Yeah. That is what we will do in the next lecture. Till then, it's bye from my side. Thank you.